In this lecture, I will discuss measurement and data collection in quantitative research. The purpose of measurement is to produce trustworthy data that can be used for statistical analysis to answer our research questions and hypotheses. But before we can start with data collection and measurement, we need a good conceptual framework. This also means that we need conceptual and operational definitions for our variables. A conceptual definition is the theoretical definition of a specific variable, whereas the operational definition describes how we will measure that variable. The learning objectives are to describe measurement, to determine the levels of measurement, identify possible sources of measurement error in published studies, critically appraise the reliability and validity of measurement methods in published studies, and describe the steps of the data collection process in quantitative research. In quantitative research, measurement means assigning numbers to objects or people to designate the quantity of a specific attribute. The advantages of this is that it removes ambiguity, information can be reasonably precise, and it is a specific language of communication. There are various concepts of measurement theory that we have to understand. The directness of measurement, measurement error, level of measurement, reliability and validity. And we are going to discuss each of these concepts separately. Variables are measured either directly or indirectly. Direct measures are concrete things such as oxygen saturation, temperature, weight, length of a person. You can even collect blood from them and measure certain blood values. Indirect measures are measurements of abstract concepts such as pain, depression, coping, self-care and self-esteem. These things are not physical, it cannot be seen, and this is usually where we use various scales that has been found to be reliable to measure these abstract concepts. A single measurement strategy can really measure all aspects of a concept. You will remember from the PowerPoint on research designs that I said construct validity means that we accurately as possible need to measure this concept that we've described in our conceptual framework. If we only use one measure to measure this concept, that is termed mono-operation bias, and that is a limitation for construct validity. In this example, you will see that the researchers are trying to measure the concept of pain, and that is illustrated by the outside circle. Now, they're trying to use three different measures to measure pain. The FACES scale, which is a visual analog scale that you give to the patient, where they self-rate their pain. You can observe their behavior to see if it seems as if they have pain. And you can also look at their physiological measures, for example, their blood pressure and their heart rate. You will see that there's some overlap in these different measurements. And the more measurements that you do, the more accurately you will predict or measure the concept of pain, because you will fill up this circle. If you only use one measurement, for example, you only use the FACES scale, you will see that you will not really fill this circle, which we in this case demonstrating as the concept of pain. So the more measurements you use, the more accurately or the more likely you are to accurately measure the concept of pain. This is why multiple measurement methods is sometimes used to describe a concept. And the more methods that we use, the more accurately we may measure the concept that we wish to measure in a specific study. Measurement error is the difference between the true measure and what is actually measured in the study. When you observe a score, when you measure a score in a certain study, you can say that it's a true score plus and minus some degree of error. And we don't always know what that is. The factors that can contribute to measurement errors in research studies is situational contaminants. There may be something in the environment when you administer a questionnaire, for example, that leads participants to respond in a certain way. Response set bias is when participants, for example, would only select strongly agree or strongly disagree, and they will respond in that specific way only. Transitory personal bias, personal factors could be people that feel very tired on a specific day, or they don't feel very well, and therefore they cannot concentrate and they don't read the questions very well. And then your item sampling. It may be that you have items in your questionnaire that does not really measure that specific concept. And that is why you need to look at that very carefully before you administer or decide on a specific questionnaire. Measurement error can be divided in systematic errors and random errors. What we usually expect in a study is some random error, which means that there's no specific pattern in the difference from the mean or the variation around the mean. With a systematic error, there is a specific variation in a direction. So that will then change your mean score either positively or negatively, and we don't really want that. And we have to investigate for systematic errors in a specific study. Systematic error would be when you, for example, want to measure patient satisfaction and you select patients who you think may be satisfied with services. That will obviously shift the mean satisfaction score in a positive direction. It may also be that systematic errors are caused by a problem with your measurement. So if you did not calibrate your BP machine, it may be that all the participants that you have in your sample have a blood pressure that's either higher or lower than expected, and that is a systematic error. When we do measurement in quantitative studies, we usually assign numbers. So it's very important that we understand the different levels of measurement. You get nominal measures, ordinal measures, interval measures, and ratio measures. And this is very important when it comes to statistical analysis. The level of measurement of a variable determines the type of statistical methods that we will use to either describe the data and also to then do further statistical tests in our study. And we're going to discuss each of these levels of measurements in the next few slides. The nominal scale is the lowest of the 4 levels of measurement. It consists of different categories. These categories are not more or less, but they are distinctly different from one another. They're also mutually exclusive and exhaustive, and they are named. Here you will see an example of nominal data. You will see that some of these categories are numbered. However, with nominal categories, the numbers don't have any inherent meaning, but we do have to assign numbers to all our variables in quantitative studies. We also call this coding. Other variables you will see, here you will see gender, male and female, 2 distinct categories. Hair color, also different categories, but with no specific order. Where do you live? The area where people live. So all of these categories don't have any specific order. They're distinct and they're mutually exclusive. Other examples is patient diagnosis. There's also race and marital status, but you will see with race, I've put a little bomb there, and we have to very carefully consider the use of race in research studies. And if we include race as a variable, we must justify that very carefully. The next level of measurement is the ordinal scale. So ordinal tells you that there's some kind of order or ranking imposed on categories. However, the distance between these rankings are not equal. We cannot really measure them. We cannot say the one is 2 times or 3 times the other. We do use numbers to preserve the order, and we call this ranks. So examples would be a Likert scale. So you will see these measures will, how do you feel today, ranges from very unhappy to very happy. This is an example of a 5-point Likert scale. The same with satisfaction, from very unsatisfied to very satisfied. Other examples is grades. For example, if you get an A, a B, a C, or D in your studies, or health status, from excellent, average to poor. Or if you have asked people to rate their health-related quality of life, from being very well to very unwell. So those are all ranked. We can say that we understand that the very unhappy is sort of on the other end of very happy. So we understand that there's a ranking, but we can definitely not say that there's a specific distance between these different categories. When it comes to the interval scale, this is where we now use numerical data. So usually this will be a number that is collected in the data. This means that we can measure the numerical distance between variables, and there's equal distances between intervals. With the interval scale, there is an absence of a true 0 point, so 0 does not indicate the absence of that specific condition. An example here is temperature. A 0 temperature doesn't mean no temperature. And the same with time. If the time is 0000, then that doesn't mean the absence of time. Lastly, we have the ratio scale. It's the highest form of measurement. It's also a numerical value that exists on a continuum. We can have an absolute 0 point, meaning that when the value is 0, that specific variable doesn't exist, or the absence of it means the absence of that variable. Examples are weight, height, age, annual income, commute times, and test scores, and there are many other examples. Here we have a question. Grades on a multiple choice final exam are an example of which level of measurement? The ordinal scale, interval scale, nominal scale, or ratio? And the answer is ratio, because it's the highest level of measurement, and obviously the score can be 0. Sometimes reference measurement or norm reference testing is used in a specific study. Examples of norm reference testing would be the weight and length Z-scores that have been developed for assessing weight and length in children. And there are specific charts for boys and girls. And those have been developed over years of research to establish those specific norms. The same can be done with, for example, an IQ test. And there are various other standardized tests that can be administered in a specific study. It is important, though, to remember that each country's demographic profile differs, people differ in a country. So it's important that these norms must actually be specific for a country or population group, and we cannot just apply norms from one country. For example, a high income country doesn't always apply to the norms in a low income country. We also get criterion reference testing, where we compare a participant's score with a criteria of achievement that includes the definition of target behaviors. When behaviors are mastered, the subject is considered proficient in this behavior, so it's a mastery test. One example is a driving test. So there's a specific score that must be achieved on that test, and that score then indicates that the person is now competent in that test. Reliability testing is concerned with how consistently the measurement technique measures the concept of interest. It's important that a measurement is dependable, that it's consistent, that it's accurate, and it's comparable. When we do reliability testing, it is expressed in a correlation coefficient. 1 will mean perfect reliability, whereas 0 is no reliability. The lowest acceptable coefficient for a well-developed measurement tool is 0.8. There are 3 types of reliability: stability, equivalence, and homogeneity or internal consistency. Stability is concerned with the consistency of repeated measures. We also call this test-retest reliability. We will administer a specific questionnaire to a participant and then repeat that questionnaire, the same questionnaire, a week or 2 weeks later. Then we will compare the answers of the first and the second questionnaire to see if there is a correlation or consistency between the two. Equivalence is focused on comparing two versions of the same instrument. We also call it altered forms reliability. Or we can look at two observers and compare their scores. That is called inter-rater reliability. One example of inter-rater reliability is when you will have two people assessing someone in an OSCE using a specific instrument. And then you will compare the scores that the two observers gave to see if they are correlated. Homogeneity or internal consistency addresses the correlation of various items in an instrument scale. So this is very specific to instrument scales that have been developed, and usually this is tested using a Cronbach alpha coefficient. We must always appraise reliability in a study. The questions that we can ask is, what reliability information is provided? Did the authors include reports of the reliability of the instruments they used from previous studies? Did the author perform a pilot test? And did they report on the reliability of the specific instrument that they used in this study for the sample that they included in their research? At the end of this PowerPoint, there's an activity where we will appraise research articles and we will specifically look at how the authors reported reliability. Here's another audience response question, and this concerns measurement error. Now you will remember that we get a systematic measurement error and we get random measurement error. The question here concerns an example of random measurement error. The options are A, actual measures smaller than true measure. B, including elements of hope in a measure of self-concept. C, measuring blood sugar immediately after breakfast. And D, punching the wrong key when entering data into the computer. Now D is an example of random measurement errors. And if you look at A, B, and C, they are all examples of a systematic measurement error.